Emission spectra. So after an atom is excited, sometimes it releases energy to make it go down. The electron emitted is equal to the energy difference between the two levels. The energy is emitted as a photon of EMR. It will show up as a bright line in the emission spectrum. So absorbed energy can be emitted all at once, the maximum energy of the photon, and as the electron goes all the way down to the ground state, or the energy can be emitted in more than one photons along the way down. So if you have an electron existing at energy level 3, if you take a look at the two different arrow paths that the electron could jump down, it could make a giant jump down from E3 all the way down to E1. And in that case, we'd use the energy difference between those values. But that's not always the case. Sometimes it'll make a smaller transition and jump down to 2. Then if it has some energy that wants to get rid of, it can jump down to the other jump as well. So technically, there could be 3 potential emission lines on our spectrum. In this case, they're only showing 2. They're showing the 3 all the way down to 1 and the 2 down to 1. This one here, this energy jump, which is energy transition from 3 to 2, has a smaller energy. And it's so small, in fact, that it would probably exist somewhere outside of the spectrum. It might be released somewhere over here. So we don't actually see it because it's going to be smaller energy than the visible spectrum. And we could do a double check to make sure that it won't fall in that spectrum lines. So let's go ahead and try that one out. So if a photon or an electron is making a transition from 3 to 2, it will release a photon. So each one of these, if I were to show this properly, you can kind of imagine that as this electron jumps from E3 to E1, it will produce or release a photon. The photon will then be released. I'm just representing a photon as this wavy green line here. And in this case here, as it goes from 2 to 1, it will also release a photon. So releases a green, releases an orange, and that's why we can see it on this black background spectrum. So it's emitting a green, emitting an orange. So once again, let's see where the smaller one, E3 to E2, where would that transition be? So to do that, we are going to use our change of energy, and we're going to say final minus initial, EF, minus EI. The final in this case is our E2, which is a negative 9.91 electron volts. And our initial was at a higher energy level, negative 9.56. So quickly, 9.91 minus a negative 9.56. And what you'll notice here is we get a negative 0.35 electron volts. And that negative just tells us that the atom is losing energy, which makes sense. It's losing a photon of energy. So in this case here, if I wanted to solve for the wavelength, I would do the same equation that we did previously. If E is equal to hc over lambda, lambda is equal to hc over our energy. Go ahead and type in our 4.14 to negative 15. Speed of light, 3 times 10 to the 8. And then divided by 0.35. I'm using the positive value in this case. Because once again, the photon has positive energy, the atom itself has lost an equivalent of that. So I gotta go 0.35, I end up getting a wavelength of negative 6. So that's 3,549 nanometers. So I was a little bit off in my picture, so I would imagine that is actually even larger than that. It would be like quite a big difference. It'd be somewhere over here in terms of that spectrum. Okay, so because it is beyond red, I would consider this to be roughly into the infrared side of the spectrum. Okay, large wavelength, roughly in the infrared.